a line that's true size and shape, if you're looking at it here, if I rotate it 90 degrees, how does it have to appear? You're looking right down it. It has to appear as a point. True size line will always appear as a point in an adjacent view. That's how you know they're true size. So if I take this guy, I see a line right here. Okay. Now I'm going to rotate it into the top view, and I see that same line now. It's actually going to rotate to here. There it is right there. Do you see it as a point? Okay. No? Well, that same line is here. Okay. Now I'm going to rotate it at 90. It's actually sitting something like this. And I rotate it, and I see it here. Okay. Is it true size and shape? I don't know. Okay. But you can tell real quickly, because I'm worried about this line. Well, what does this do and this do? Those define the edges, don't they? So think of these lines. So if I take this one, rotate it 90, how do I see it? The point. I take this top one, I rotate it 90, how do I see it? As a point. So what that tells me is that in this view, this one's true length, that one's foreshortened, that's foreshortened, that's true length. In this view, this one is true length. I don't see anything else. This one's foreshortened, that's true length, that's foreshortened, that's true length. And I use the fact that a line, if it rotates, a true length line always appears as a point in the perpendicular or adjacent view. So it's a way for you to break things down a little bit further and not deal with shapes, but deal with lines. In essence, that's what this one's trying to tell you. Which ones are true shape, which ones aren't. And you know it two ways. On a plane, if a plane appears true size and shape in one view, as an edge in all adjacents, got to be true size and shape. The entire thing is. If you are dealing with an inclined plane, you know it will not all be true size and shape, but portions of it may be. Look at the lines. Any of those lines that appear as points in adjacent views must be true size. Yes, sir.
I don't understand why you refer to it as a point instead of
Because it appears as a point. So here, this one. Here, that's an edge, right? So I'm going to use this ruler to represent this. It consists of 2 points, right? A line, shortest distance between 2 points. So here it appears as a line. I rotate it 90 to that location, that's where it is. Now it appears as a point. That line has to be true length. Has to be. Because if it's not, if it's at any angle like this, and I rotate it, it's going to come up something like this. I'm going to see it foreshortened, where it projects, you know, kind of like you can see my shadow here, if I can get this thing correct. Like that. The only way that happens is when they appear as points. So in essence here, you're looking at planes and lines and trying to determine true size. Now, why would that be useful for you? I mean, if you look at it and say, I know I'm true size here, you're going to be true size here. So you know the size of it. When you look at the object, you can kind of start building those pictures in your mind. So you're looking or analyzing lines and planes for true size and shape in number 3. Number 4, this one's just the opposite. Features are foreshortened when the lines of sight are not perpendicular to the feature. I mean, it's pretty obvious on this one, I think, in my mind it is anyway, is that if I take any plane and I rotate it and look at my shadow, that thing's foreshortened as you see it, and that's how it's going to project right on the, as the shadow looks on the board. Now, I am always looking at it here or there or whatever. No matter how I rotate this, I'm never going to see it. This would be this view. It's going to be an edge, so it's an incline. Well, the top view, what's it going to be? So I'll go back to here, and then the top view is going to look something like this. There's different shapes, but if I locate what's true size and shape, anything that's not true size and shape will be foreshortened. So in essence, 4 is a result of number 3. It might be the best way to put it. By the way, is anything larger or appear larger than it really is? It will never happen in an orthographic view. Everything is true size and shape or smaller. Okay? It's never larger. Any questions on that one? 3 and 4 are really the same thing. Number 5, configuration of planes. Areas that are the same feature will always be similar in configuration from one view to the next, unless viewed on edge. Or, the surface with a given shape will appear in every view in a similar shape unless they appear as an edge. Let's go look at this figure. This is page 523. Now this one in my mind doesn't really help you draw, but it helps you analyze. What it's basically saying, if I have a plane that has 4 sides, unless I see it on edge, it will have 4 sides in every view. It's not going to grow another side, and it's not going to reduce another side. They will always have 4. Here we have 2 planes. We've got an inclined plane and an oblique plane. How do I know B is oblique? A definition of oblique plane, you never see an edge or true size and shape. And you notice on B, we never see those things. So in essence, what it's saying, B, it has 4 sides here. Now, unless I look at this on edge, it's going to have 4 sides in every single view. Here it is. Okay. Again, doesn't look identical, but it's still got those 4 sides. This one looks very close to this one. In fact, it's a mirror image of it. Still has 4 sides. To show how that changes, that's an oblique. We'll never see an edge. If I look at C, which is an incline, here I have 4 sides. Looks like a rectangle. Come over here. I got pretty much the same rectangle, 4 sides. Here I see an edge. That's the only time that will ever appear without 4 sides. So if you did another view, it needs to have 4 sides or be an edge. All foreshortened surfaces. Obliques, by the way, you will never see on edge. So in essence, that's what this is saying. Those planes don't change from one view to the other. They will appear quite similar in several views. Number 6 kind of goes along with number 5. Parallel features are parallel in all views. We're using the same one. So if I look at this view and I see this top right here, and I see it's parallel here, well, folks, it's got to be parallel everywhere unless viewed on edge. And then it's still parallel, you just don't see one of the lines. So there's parallel, there it is again, parallel, here it is again, they're parallel. Have to be. Now this is true for every plane. Normals, inclines, obliques, always. If your geometry is parallel, it will always stay parallel. That's not true in perspective drawing, it's true in orthographic drawing. Do we need any more on that? It's kind of the same as one before it. Edge views, number 7. We're going to page 524 on this one. Surfaces that are parallel to the line of sight will appear on edge and are represented as a line. Okay. This is kind of back to number 3. And all it's saying is if you look at any plane on edge, It appears as one line, no matter the orientation. Here, here, whatever. And they kind of give it out here. So here we have an inclined plane like on this guy. But when we rotate that, we will see edge views. Okay, so there's an edge. I don't see any foreshortened surface there. These are all true size, angles true. The thing that this is important for is if you look and you say, oh, you know what, I know that line right there is foreshortened. Well, what that means is your angle will not be true, because it's not a true size line. So in essence, what you're looking for here, if you have a true size plane, normal plane, and you see it, all the angles on it will be good. When you get to an inclined or an oblique and you look at them as foreshortened surfaces, you cannot trust the angles, you cannot trust the line sizes. So you got to start analyzing them and saying, is this line true size? Is this one foreshortened? If you have an inclined plane and two of them are true size, so let's look at this plane right here. Okay. We see it as an edge right here. Are any of these lines, these three, are any of them true size? Remember, you know a true size line because it will always be a point in an adjacent view. Okay, so let's look at it. So I've got this line right here. How does it appear? It's a point. Okay. So this line's true length. So we know that's true length. This line. Still going to appear as a line, right? But now it's here, so it's foreshortened. So I know that this guy is foreshortened.
Wait a minute, do that again?
I'm going to the top view. In the top view, it projects like this,
How do you know?
because it's drawn right here.
How do you know that you just said that?
It's actually sitting on here like, can you see that angle I've got? It's not on the board, it's angled back into the thing. So when you rotate to the top view, it appears like that. So now I've kind of got the angle on it. It's foreshortened.
Okay, question though, if you didn't have the top view driven and you saw that, how would you?
You wouldn't know.
Okay.
You would have to have another
Okay.
view. Yeah, you can't tell this stuff in one view.
No.
Okay, so that one's foreshortened. Is this one foreshortened right here? Right here? How does this project? It actually projects in a line, right? So the thing's got to be sitting like that, and it's right there. Okay. So again, it is foreshortened. Now what that tells you, is this angle right here really 90?
No.
No, it's not. Well, it could be. We don't know. Is this angle really what it is? Don't know. It's got a foreshortened line on it. Now, if you had two true length and true length, you can trust that angle. But you can't unless both lines that define the angle are true length. So in essence, that's what this one's telling you. What can you see and what can and trust and what can't you? Now, you're kind of figuring this out, I think. Inclined and oblique planes cause a heck of a lot of problems for the glass box. I mean, the whole point of doing orthographic projection is what? To get true size and shape to build off of. We're seeing some holes pop up here, aren't we? Okay. We're going to solve those in a week or so. But for now, the thing I just want you to know is that this thing is not the catch-all for everything. It is our go-to drawing style, orthographic projection, technical drawings. We use it every discipline. But it does have some holes. And we need to know where those holes are. And in essence, they occur when you get inclined and oblique lengths. That's where your holes are. All right, let's keep moving on this. Any questions on that? Contiguous areas. This one, boy, I had to practice to say contiguous. No two contiguous areas can lie on the same plane, or no two adjacent areas can lie on the same plane. And we're going to go clear to the end of the chapter for this. Let's use figure 1081, although I list 3 of them because the author uses 3 on here. What this basically says, if you have some planes identified in one view, they cannot overlap into other planes in other views. Okay. So in essence here, I have C, plane C. It's this little nose that sticks out, right? Well, this C has to be in every view, and it cannot intrude on other planes. And so you go and find it, it's here, okay, it's all good. But that's going to help you because C only goes right here. Right? This is not all the same plane on this edge. You've got plane C and where BD comes down. Not BD, it's actually B, if you read the one before this. Pretty common sense, it seems like. Plane will never intrude into another plane, but when you start projecting, you get that occasionally. You miss a line or you pull a bad measurement, and all of a sudden you've got plane B sitting halfway into plane D. Well, that's the key. You got a mistake somewhere, and we need to track that down. This one's kind of an analysis at the end, or even at the start to help you visualize. If you come back and look at this, the author starts over here by taking a 3-view drawing and just assigning arbitrary letters to it to help them identify where these are at. And then we came into 1081 where he started joining them and saying, oh, these are all the same planes, just shown in different views. So no two, or planes that sit by each other will always sit by each other. That's kind of another way to say that. Any questions on that? All right, folks, laws 1 and 2 are the ones that are really going to lay this out for you. Laws 3 through 8 are analysis. Leave one for back into her. Yeah, we're going to do a little bit. So. Has anybody done a missing lines worksheet before? Sean, you have? These are fun.
Oh, yeah.
All right, I did put another drawing on the board for you. I would like you to focus on the worksheet I'm handing out now before the drawing, because the worksheet's going to help you with that. Now, with that said, if you did 8 hours of this, probably entering you into a mental institute tomorrow morning. So do this for a little while till you need a break and then go to your drawing. Okay. Now you do have a deadline of G2. Well, no, today's only Wednesday, right? So you got another day on that one too. Now, how do you do these? In essence, as you look at these, you're given 3 views in each square. So let's look at number 1. Which 3 views do you think I have?
Okay.
Yeah, our 3 primaries, front, top, and right. There will be at least 1 line that is missing in the projection. So you need to find that and institute the line. It may be an object line or it may be a hidden line. Okay, we don't really know at this point. Now, number 1 is fairly straightforward because they give you an isometric of it. Okay. But really, the way you want to do this, folks, is kind of analyze it. So first, look at your surfaces, or 7 and 8, right? Start looking for surfaces. I got 1, I got 1, I got 2. Okay. If I'm looking here, I got an edge, edge, edge. Do I see all those edges out there? Okay. Now, the other way to do it is just start drawing lines. Right? Well, I know that line's up, right? That's rule 1. Does that look good? For now it does. You bet. Okay. Then I come this way. That one looks good. That one doesn't. That one does. Okay. Now, I found a projector using rule 1 where there's nothing here. There has to be something there. Has to be. Because I've got a line, which is a point and a point. Rule 3 states a point in one view has to be in another view. There's got to be something here. Now, what I then have to do is figure out what's missing. Well, I bring this up. Well, there's the line I'm missing, right? From there to there. Okay, so I know I've got a line here, I just don't know how it sits. So let me draw my meter in. I know it goes from here to here, and it goes from here to here. There it is. That's an OBJ. That's the line that's missing.
Why would you have to do the meter? You wouldn't just have to come off the front view?
Because you got to find the extent of it. We're going to do one that doesn't have an isometric on it, so you can see this. Okay. So that's overall how you do these. Okay. Let's look at 13. Okay, so here's your steps. There's no isometric here. There's my other point. Boy, doesn't look quite right. There's right there. Okay, so there's my meter line. Okay, so again, I'm going to project. That's good, that's good, that's good. I'm finding stuff there. I don't know that they're right, but I'm finding stuff. Okay. There's my top, there's my bottom. Here's my line that's missing. Okay, didn't hit anything in that right side view again. Now, once you do that, you know you're dealing with this area right here. Now you just have to figure out the extent of it. I look in this view, here's that same surface, right? Because there's a point. I use rule 1 to know that it sits here, and I know it sits here. That's, both of those are rule 1. Now I need to use rule 2, or equal distance and related views, to determine where it's at. So I'm going to bring those over. I find that it's the extent here. Bring this one down. There's the extent there. So there's the line. So just so you know, and you can see the rotation. So I'm a point. I'm a line. By the way, is this line true length?
Yes.
Yes, it has to be, because it appears at a point here. That has to be true length. Okay. It's got to be a line over here. And all the way, by the way, it's true length here too. Now, the only thing we then determine, can I see it or can't I? No, I can't see it because this is in my way looking from the right. That's a hidden line. Clay works awesome on these. Some of these you're going to find fairly quickly. Some of them are going to twist your mind a little bit. Go to the 8 rules of orthographic projection. If you aren't seeing it, your next step ought to be immediately to start running laws 1 and 2. Then start looking at laws 3 through 8. I can't get it there. I'm going to some clay, and I'm trying to model this thing so I can turn it and twist it and help my mind wrap itself around with these rotations that are going on. Have fun with these. If you get stuck, feel free to work as peers. Don't let somebody else do your work for you, though. Understand what's going on. If you can't get it as a group, get me involved. This is my weak spot, I'm telling you right now. This mechanical engineering field is my weak spot. I'll struggle right along with you. I've yet to find one that I haven't figured out. Sometimes it takes me an hour or 2.
10.
Yeah, and how do I figure it out? I do 2 things. I go to the 8 rules of orthographic projection, and I go to clay. Those allow me to figure it out.
Can we have some clay?
Yes, we do. Last year's class left a bunch in that little miscellaneous drawing folder in there. I mentioned the other day, maybe you want to do a club expenditure and take $10 out. You could go take $10 out of your club funds, go to Walmart, and you would have enough clay for everybody to use this year. If you, and The other thing is, I think it's a good idea because I will allow you to use visualization tools on a test. And so if you use something like Clay as a visualization tool, and we've got it as a global deal, unless everybody's got enough, I'm gonna cut it for everybody. So you may make sure you have your own, I guess would be my thought. I do a toss of $1 for enough Clay to last you the whole year. But you don't need it, there's some back. Me and Lisa went through it this morning. Threw all the stuff that was too hard to use anymore away, and there's still some there. All right, with that said, that's all I'm gonna cover today. You do have G2 due tomorrow, G3 will be due Friday. If you have any questions on that one, I'm not planning on really introducing that drawing until tomorrow. And tomorrow, we're gonna start looking at, the rest of this week actually, how all the different shapes project that are in this chapter. I'm gonna do some drawing for you tomorrow also, because you haven't really had a chance to see how somebody would put one of these together other than just what the text is showing you. So I'll do a little bit of drawing in tomorrow's lecture also. All right, thanks for your time. Ask questions as you go through the day. Let's have a productive day. What did my old man used to say? Let's make some hay.
Are we turning this in?
Yeah, that will be turned in. Yes, that's going to count as a worksheet on your grade. All right, thanks for your time, folks.